All right, here we are. We'll work on example 2. And we're going to use this next theorem. As you recall from the last term, we constructed the series, Maclaurin series, from the given function using derivatives and values of derivatives at a center point, which was for the Maclaurin series, 0. So, but we don't know that series converges to the cosine. That's what we had, because the theorem doesn't tell us that. This is a theorem that fills in that gap. If we have a series, a Taylor series, okay, which has this remainder. Okay, remember this remainder term from that theorem back a couple sections back. We had this remainder term. If that remainder term heads to 0, then our series will converge to the function f. Okay, so that means it's we have to have the series in front of us first, and then determine if this remainder actually heads to 0. If it does, for any x on that interval, then that means that series that we have in front of us will actually converge to the function itself. Okay, so you might have a convergent series in front of you, but you can't verify that it actually converges to the function that you use to create it, in a sense, because it could be another function actually that has the same derivatives as the original function at that point that we centered the series about. So it is possible that that can happen. So this will guarantee that that doesn't happen if we can show. So, and this could be challenging in some problems. So what we're going to look at is that, see if we got enough room here. Maybe we got to use another page for that. Okay, let's add a page. So what we have to do is we have to take this remainder term and put a bound on it. First of all, well, it's equal to, in this case, we have n plus first derivative evaluated at z. We have n plus 1 factorial. And we have x minus c to the n plus 1. Okay, and we saw that this thing can never be bigger. And that is for some value of z that's between x and c. Okay, so that's what the Taylor's theorem told us back a couple sections back. Now, we're going to put a bound on this in this case. This would be less than or equal to the maximum of and then we have this thing here. Okay, so the idea is that let's get a handle on this thing, the derivative. We know for this function that we've seen that the derivatives we saw from the last example, that these derivatives are going to be either going to be plus or minus sine of x or plus or minus cosine of x. So this function, this derivative will never be bigger than a 1. Okay, the absolute value will never be greater than a 1. So we already have this that we can see. For this function. And at this point, we should indicate that we are working about value C. See, that was a 1. For our case, we have C equal to 0. So this is what we're left with. Okay, now, if we can show, the idea is finding the limit for this. Our remainder term is less than or equal to this term. So when we go to find that, the limit of that remainder term, this will be less than or equal to this limit. Now, we saw a little bit about this one back in section 9.1 when we saw this type of limit. Back then we were looking at things like this, 2 to the n over like n factorial. We were examining what happened to this limit. And although we're not going to show this, we did show that this limit does go to 0 for this value. But in general, what we have here is a constant raised to a power divided by n plus 1 factorial. So it's the same form in here. And it's been shown that this type, this exponential function divided by the factorial, ends up being a 0. Okay, and again, we did show that that was true for one case, I think, back in an example. I think we did this one, the 2, maybe the 3, I don't remember. Anyway, so over here we have a constant. This is x is some value. I mean, you would do this remainder term. You can check for any value of x that you want, and it's not changing. It's variable, but we would check this for any value of x, and this thing would head to 0. Okay, so we'll have to take that on faith at this point. We're not going to show that this is true for any value of k to the n over n factorial. That limit, it does head to 0. We saw individual cases for k, but basically the idea is that you're always going to have the k's matching up. The number of k's with a number of factorials, and eventually, whatever value k is, eventually the n will be bigger than k, and that term, the expression will head to 0 eventually. So let's see. We have enough values of n big enough to create this, force this to 0. Okay, so this does head to 0, and that means, okay, so we've shown this thing does head to 0. Oops, not there, here. Okay, get that. This does head to 0, which means that our series that we found for the cosine does converge to the cosine. Okay, so that means that series that we had is minus 1 to the n, x to 2n factorial, like that, converges. All x in here.